We'll be talking about conservation of energy using spring potential energy. Uh, in this question, we have a car uh, that is about 130 kilograms. So we know that the mass of this car is 130. And the car is compressing this spring. So this spring is actually being squished backwards like this, and it's actually going at a distance. It's actually compressed um, about 3.2 meters. So you're actually given X. They also tell us the spring constant. It tells us how stiff or how elastic the spring is. So they give us the K value, which is 1,400 newtons per meter. All right. Now, once the spring launches the car will actually travel up the incline a certain distance. And the question is asking how far up the incline did the car go? And so the car will go all the way up and pretty much stop about here. And we want to know exactly how far up this incline it is. So we're actually looking for the distance up this incline. Now, you'll notice the first thing we need to kind of figure out first is because we're dealing with conservation of energy here, we need to look and analyze at the types of energies that we're seeing. The first one we need to keep in mind is that whenever a spring is compressed or elongated, you're actually storing it in the form of what we call potential energy due to the spring. So this is the second form of potential energy that you need to be familiar with. The other form of potential energy is potential energy due to the height, which we'll actually talk about in just a moment. But potential energy due to springs is another form of stored energy, and you might want to know the equation for that. The equation is 1/2 kx squared. Now, if you don't like fractions, you can turn that 1/2 to 0.5, or I just like to say kx squared over 2. And this is the equation for potential or for spring potential energy, where k is the spring constant and x tells you how far the spring was compressed or stretched. All right, that's the only energy that's happening at this point. Okay. Now, when we let go, the spring will launch the car in this direction, and eventually, all of that energy has transformed into kinetic energy. So at this point, at the bottom of the incline, right as the spring lets go of the car, the spring is actually, or not the spring, but the car is now moving at the fastest maximum kinetic energy. So you could say that the potential energy I store up here due to the spring potential energy that I store there is eventually how fast I'm going to go at the bottom of the first hill. So we can say that the spring potential energy is equivalent eventually to the kinetic energy at the bottom of the hill. We can say that this is situation 1, this is situation 2. So we can say that the potential energy of the spring on situation 1 is equal to the kinetic energy in situation 2. Now, at this point, it's going at the fastest speed possible. Well, eventually, that's going to actually go away because it's going to go up an incline. And as you go up an incline, you'll notice that the speed decreases, and at the same time, our height increases. So basically, what we're seeing here is that we're losing kinetic energy and gaining potential energy at the same time. So we're actually starting to see a transition of all of the mechanical energy, and it's transitioning from kinetic to potential. And it'll come to the point where it actually stops because it's too high. The energy that we produce down here is not good enough to complete the entire incline, which probably might still be going further up. But at some point, the car is actually going to stop. And we want to know how far up that incline goes. We can say that at this point, when the car stops, there's no longer any kinetic energy, which means that all of the energy has shifted to potential energy. So that at the top of the incline, or at the top of whatever point the car stopped, all 100% of that mechanical energy has been focused or been given to potential energy. So we can say that whatever kinetic energy we formed down here, or whatever kinetic energy that we got from storing the energy as potential energy of the spring down there, whatever energy we have down there, that's eventually how much potential energy we're going to store when we get up to the second hill. So, or as we get on top of the incline, on top of the incline. And so this could be labeled as situation 3. And so we can say that the kinetic energy that we have at the bottom of the incline is equivalent to the potential energy at the top of the incline, which is where situation 3 is at. And so we can say that all 3 are equal to each other. Whatever potential energy we store down here, that's how much kinetic energy we're going to get at the bottom of the hill. And then whatever kinetic energy we get at the bottom of the incline, that's exactly how much potential energy we're going to eventually store when we get to the very, very top, where the car is no longer moving, but it's at the top of the incline or near the top of the incline. Okay? Now, our goal eventually is to solve for the distance, okay? And we're going to get to that very shortly. But keep in mind that this right here, solving for the potential energy at the top of the incline or wherever the car stopped, is key to solving for how far up the incline the car went. Okay? Let me go ahead and clean this up so that way you can see this a little bit more better. Okay, so this is what it comes down to. We're equating all of these energies together. We don't know much about the kinetic energy. However, we do know that whatever potential energy we store up here, that's how much kinetic energy we have over there. So these two, if the potential energy equals the kinetic energy at the bottom of the hill, and if the kinetic energy at the bottom of the hill is equivalent to the potential energy that we store back up on the top of the hill, then we can ultimately say that the potential energy that we store due to the spring is equivalent to the potential energy that we will store eventually again due to the height. And so the equation can actually be simplified to this: potential energy of the spring is equivalent to the potential energy due to the height. And so that's what it comes down to, and we're going to use that to solve for our potential energy due to the height. Now, you'll notice that these can be broken down, and again, I'm going to actually break it down to the equations that they stand for. So this one actually can be broken down to the equation, potential energy of the spring can be broken down to the equation kx squared divided by 2, and then potential energy of the height, that actually can be broken down to mass times gravity times height, where height is what we're trying to solve. Now keep in mind, height is not the final answer, but it is the bridge, the key to finding the distance along the incline. And here's the reason why. If we know the height by, which is from here to here, okay, if we know the height by using this equation, just manipulating this equation around, if we can find the height, you notice that we found one side of the triangle. In this case, we happen to have found, if we find the height, we will find the opposite side of the triangle. The distance up the incline, which is this right here, is actually related to the triangle's hypotenuse. And if we know our opposite and our angle, and we need to solve for our hypotenuse, we can eventually use the equation sine of theta equals opposite over hypotenuse. Now we're going to actually solve this equation in just a moment, but first of all we need to get our opposite, which is our height, in order to actually use the equation to solve for our hypotenuse, which is the distance along the incline. Okay, so we'll get to that a little bit later. Let's go ahead and solve for our height first. So we're going to use our conservation of energy equation, which is this thing down here, to solve for it. The first thing I'm going to do is I'm actually going to divide mass and gravity on both sides of the equation, because I'm trying to get height by itself, and so height equals kx squared divided by 2mg. So that would be k, I believe I wrote the number up here. K is 1,400 newtons per meter. That's our K. Our X is, let's see here, 3.2 meters. That's how far the spring was compressed. And I'm going to square that because the equation tells me to square it. So notice I'm setting it up like that. And then I'm going to just plug in the values for the bottom. So I have 2 times the mass, which is, I believe, 130 kilograms. That's the mass of the car. So we're going to say 2 times 130 kilograms times 9.80. All of that will give you my height. So let me go ahead and solve that. And as an answer, we get 5.27 meters, because meters is the measurement for height. And so this tells you how far or how high up the incline my car went. So we can say that the height is 5.27 meters. Height is 5.27 meters. And what we just solved was the opposite side of the triangle, and then all we need to do now is solve for the hypotenuse. So again, we're going to, this is our final step to find the actual answer, which is the distance up the incline. That's our hypotenuse. We're going to use the equation sine of theta equals opposite over hypotenuse. Now, just in case you don't know that equation, first of all, you got to remember, what do you know from the triangle? Know the sides of your triangle. The bottom side is the adjacent. We don't have anything about that, but we do have the opposite side and the hypotenuse. And if you remember your mnemonics, so katoa, the only equation out of the three that can be able to solve what we're trying to look for is our sine, opposite over hypotenuse, which is where that came from. All right, our goal is to solve for hypotenuse. The first thing I'm going to do is I'm going to need to rearrange the equation to solve for hypotenuse. Our unknown is in the denominator, so I have to put that in the numerator first. So I'm going to multiply hypotenuse on both sides. That cancels out, and so we get opposite equals hypotenuse times sine of theta. And then, of course, now that our hypotenuse is in the numerator, which is what we need to make sure our unknown is in, we need to make sure that the unknown is also isolated. So we're going to divide sine of theta on both sides. And so by doing that, our new equation is, this cancels out, so now we get something like this: hypotenuse equals opposite, which is 5.27, divided by my sine of theta. Theta again is the angle at which my incline is in. So I look down here and I see that my inclination angle is 23 degrees. So I'm just going to plug that in. So it's going to be sine of 23. And all we're going to do right now is just solve for it. So our hypotenuse is that divided by that. And so our answer is 13.487, which we can say 13.49, or you can just say 13.5. And hypotenuse is the distance up the incline. So that's how far up the incline the car has gone before it actually stopped completely at that point.